Okay, I think it's okay. And okay, we got to the point where, well, we started with a regular Anderson model, and instead of writing everything again, we get to the point that we could find scales going to infinity with a property that for every x, the probability that a box of size Lk, there is this, let's say, some positive m, is m, I have fixed an energy, is m irregular. This was bigger than or equals than 1 over E2 minus L zeta, where zeta was L1. And this could be done, okay, so for every zeta, I can find series of scales. This also depends on zeta. Such as I have for a series of scales going to infinity. So now I want that from this, go away from a single energy and go towards the energy interval multiscale analysis. So, and I could have skipped this step, but since we already discussed it, it simplifies what comes, and I'll start from that. And what I will actually show is that for every zeta, I can find a length scale. Depending on zeta, I can find some mass, and I can find some delta, also depending on zeta, such that I get the interval around E of size delta, and then I can find scales such that if there exists, if L0 is bigger than this initial scale, and I define scale this way, this is gamma is less than 1, bigger than 1, and it has to be smaller depending on zeta, which I'll come to. I think what I really need is smaller than 1 over zeta. Then what we can show is that for those, that for every x and y in RD, such that the boxes do not intersect, the probability that a box that for every energy in the interval, either the box centered at x or the box centered at y is m zeta E prime regular, it's also given by e to the minus. I'm sorry that I'm trying to squeeze it not to have to use the other. And once you have that, you have a statement that includes all energy in an interval, and I can say something about the spectrum in the interval. Information about a single energy is not enough. You have to use something else to do it. And that's one way, is to try to put it inside. The step 1 to do that is that I have to start a starting that goes like that. And this is very simple. Suppose I take E minus E prime less than delta. Then, if I have a box of size L, and I look at the Green's function in this box at the energy E prime, this is bounded by the norm of the Green's function at E plus the difference in energy times the product of the two Green's function. And somehow today I don't seem to be able to fit anything on the board. Okay, the result for that is that so I'm going to use that in the following, maybe I'll do that here. So now, suppose, and I'm going to use the things I already have, this box happens to be M irregular, and I'll also assume, because I can calculate the probability, I have the Wagner estimate for this box at this one energy, and this was exponential L to the phi, and I always take phi between, no, actually I think I have the opposite, and zeta is smaller than phi, less than 1. Then this event, the probability that lambda L is both regular and satisfies the Wagner estimate, this one is bigger than equals e to the minus L zeta, because that's what regular means here. 1 minus, and then I have to subtract that, which you saw last time is here something like e to the n minus beta over 2 L to the phi. So this gives me, let's say, 1 to minus bigger than equals, let's say, minus 1/2 of L to the zeta. So by taking some zeta smaller, I can get rid of the 1/2. And if I give me these circumstances, then when I come here, actually, if I assume this or this, then for taking delta simply to be, and let me just tell you what I'll take instead of spending time deriving it, I'll take delta to be, let's say, this seems to work, e to the minus m to 200L. What I can prove is that it follows from what you hear is that if E minus E prime is less than delta, equals to delta, I conclude that the norm of this Green's function is actually, where did I do that one? I don't get this, but I get something that is almost as good, right? I mean, if I move a little bit, I don't change it too much, so I don't moving it too much. And from this equation, I also get that if I take x minus y in the box, but the distance over 400, this thing here is now bounded by e to the minus m for the same reasons. This is the one for E. I have the difference, and the other term I just estimate by the brute force, but I already have this estimate, so I get 2 e to the 2 of, L to the phi, By the way I have chosen delta, I end up getting here that z is smaller than 2 to the minus m x minus y. So by extending the interval a little bit, everything I know for the energy E holds for every energy in the interval, except that I got some factors which I could take care by getting rid by changing m slightly and changing phi slightly, and that's okay. So what we can conclude is that from these arguments is that with E now having the interval E minus delta, E plus delta, I can rewrite those conditions here, the conditions I have on top, this one here, with a delta that depends on k, but I'll fix it when I fix the next scale, and I have that the probability, now let me forget the prime, for every I in this interval, the probability that either one box or the other, so let me take this box to be a size which will be called L0 in the end, is M0 irregular, but now I have two boxes, but for all of them, and as always x minus y are separated, so these two boxes are disjoint, this probability I can arrange. This is a different zeta than what I use up here, but since I can do that for all zeta, I get that for all zeta. So all I really means that for these conditions, at any one of those k's, I can find an interval. The delta will depend on k, because I have the L here, but I have, and I can do it in an interval. If I want to work, if I have the single energy multiscale analysis in every energy in an interval, I'll start at some L0, and then I can actually cover it by a finite number of intervals. Maybe there are a lot of them, but a finite number. I work in this interval and put everything together and get my conclusion. But the point is that from what I know that I can obtain that the size of the interval will shrink when L0 goes large, but I can obtain that for a sequence of L's going to infinity. And this is going to be the starting, since this is the last lecture, I don't want to spend as much time in this, I want to go to the other part. I mean, from this, I will then do a multiscale analysis to get the conclusions and get it for scales that go up. I just want to make a couple of observations in how you actually do that. One key observation here, let me erase this. What did I put? I will use Wagner how I was using before, and my gamma will be actually, I think, is less than phi over zeta. And what I'm going to do, I just want to give the key idea. I have this is lambda capital L of x. This is a disjoint lambda L of y. And this is little l to the gamma, and I already know the result at scale little l, and at scale L0, I have even a stronger statement. because, oh, what did I say here? I'm sorry. I said something makes absolute no sense. That's not what I did here. I had no x and y. I only had x. So what I really prove in the initial scale that for every energy, the probability that a box is regular is good.
We have an L0 there. Huh? In the lower part, it's an L0 rather than an L.
L0, of course. And of course, the zeta should have changed slightly from the one I have up there, but I'm sorry. And from this, you can get this and this scale L0 because this is much stronger than this. If it's true for one box, it's true for two boxes. You just look at one of them. I just wrote too much here. Okay, the way we are going to do it, first, we are going to assume you take the covering that a certain number JL of bad boxes in either one of them. JL is going to be as it was for the singular energy. One, I'm going to take L minus 1, L to the gamma minus 1 zeta prime, where zeta prime is going to be chosen to be actually bigger than zeta. And this, however, is going to be different. I need to take now JL to be an odd number, so by that I mean it's more or less that, because what is going to be important to me, let me call this number SL, is that this number is going to be even. I can always take more boxes than the ones I need. I can take one more and make it an even number. The point now is that I can do I want actually so I now fix one of them, L or X, I don't care. And let me look at the probability. I want to get a lower bound on the probability that for every energy I have at most JL boxes. So I'll look at the probability that there are. So this is a complementary disjoint SL bad boxes for some energy in the interval. That's a different statement. I'm looking at the probability that there are disjoint boxes. What I want to estimate is the probability that for every energy in the interval, there are no J, which is S minus 1, right? Disjoint bad boxes. Remember that the notion of a bad box is energy dependent. And I want to estimate 1 minus something. The minus something is an upper bound for this probability. This is a complementary event to this. But that's, so when we're estimating the bad event, how do I do it? Well, if I have SL boxes, let me take all possible collections of disjoint boxes. These are okay, SL. So these are boxes in the covering, and they are disjoint. And now I look at the probability that these particular boxes are bad for some energy. Okay? I'm overestimating, but that's okay. Okay, let me do it here. you need to invent some board where you press a button and the board is clean. It's sort of surprising that you don't have them or not available. I'm sure they exist, but they're just... Okay, so now let me look that if I fix these disjoint boxes, I want, what is the probability that these are bad for some energy? Well, this is equal. I can decompose this event like lambda. Well, these are contained, so the probability is going to be smaller. I look at the probability that lambda 1 and lambda 2 are bad for some E. Lambda SL minus 1, lambda SL is bad for some energy. I can only make it bigger, right? But the point is that whatever happened here and here are independent. So this is actually the product from 1 to SL over 2 of the probability that lambda 1, lambda 2 are bad. Lambda I should put lambda I plus I minus 1.
I mean, what are the dots standing for? I mean, after lambda 2 comes lambda 2, lambda 3, or
Yeah.
lambda 3, lambda 4?
Lambda 3, lambda 4. That's why I need an even number. I took them 2 by 2, and so yeah, so I plus 1. So
Why?
my indexes are not good. Let me not worry about the index. So let me just do the result. Since the probability is the same, so I have 2 disjoint boxes of size L, and they are bad, and I should have these to the power SL over 2. Just independent. But my induction hypothesis knows what that is. That is less than e to the minus L to the zeta. So I just should multiply it by minus SL over 2. And okay, and if once I have that, I can come back here and say that what I have here is less than equals, well, I put what I have for each one of them. And here I have to put the number. Well, I know what the number is 2L over L to the D, but I chose SL of them, so I put an SL here. Yeah, the numbers of pairs, I really should put a 2D and divide by 2, but it's the same thing. And if you do the calculations with the JL that I have chosen, you are going to find out that I can make this smaller than e to the minus L to the zeta, because of my choices of SL and gamma. So I get the probabilistic estimate. So this is less than 1/2 of what I want. And then I have to take care of the other part. What can I do? Okay.
Should I pull down the back?
Yeah, I'll pull down. I can pull down the other one. I just decided to use this one. It's okay. I could actually do that. I was careful enough.
The ones on the side.
Yeah, I was careful enough not to put them as high as Frederic did the other day. Okay, so now my situation is the following. Oops. I'm going to assume that I have, let me actually put here a 4. Because then I come here and I say, if I want this in both, I can say that. I just change the 4 to 1/2 and I'm okay. This is a separate box, independent. I do it for each one of them, okay? So with good probability, I am coming and saying I have, for every energy, I have at most the maximum number of bed boxes I'm allowing. Okay, so I have JL bed boxes at most in the covering. So now, what I want to say that one of them must be good. Now, what do I need to make one good? For one of them, say this one, I need Wagner for the whole box and Wagner for the extended bed boxes, right? If I can do that, I know that I got it. I got regularity for the full box. The problem for using Wagner is that Wagner is for one single energy. And now I'm doing for the whole interval. But then we use the estimate, which I already did last time, that for Wagner from boxes, I know that if I take any box here of size, let's say, I don't want to use L, let's say of size T, and I take any box here of size S, the probability that the distance between the spectrum of H and HS, H lambda S, the probability that this distance is at least a given epsilon is going to be smaller than the Q mu to the 2 epsilon times the size of the two boxes, so it's roughly T to the D, S to the D. Epsilon, I'm going to choose epsilon like I have been doing before, e to the minus, both the T and the S are going to be bigger or equals to L. So I think I am good enough to take in this e to the minus L to the phi. So this thing here, I'm going to get something like e to the minus beta 2 L to the phi. And since those are smaller, those absorb, maybe I put a 4 here if I want to be more precise. But I can say that the distance between this box and these boxes is at least that something was wrong. I'm interested in the complementary event, of course, but we estimate always a bad event, which has more probability. This is a number like that. So the point now is that I can estimate what are the probabilities that these things happen. And that was doing, should I just skip it? I have a feeling I am going to skip it because I want to do other things. But the point is that I have a collection in the first box of roughly JL types. I mean, because I extend, I group them. Each of them of size, some constant, maybe dependent L times JL. Maybe it's JL, it doesn't matter. And I have the same here, that I have to have Wagner. And I do that for every of these boxes here to every of these boxes here. In the end, I put everything with the choices we have made. I get another half of e to the L to the zeta. But and probably, yeah, I don't want a half. Maybe I want a 2 0 or a half, doesn't matter. But the point now is that I come up here, and I already proved that I am in the, I threw away, I come here and I add Wagner between boxes, so I get rid of C, so I have the probability I want. And I say, look, I have my two boxes, here and here. I have the bad boxes inside. To finish, I have to show I have Wagners in all of one. So I say, well, if I look at them and both of them have Wagner everywhere, I'm happy. I can use either one, right? If this one is no good, so at the energy I'm working, this has too big a Green's function. I know that the spectrum of all the boxes I carry here are far from the spectrum of this one, so they have to be far from that energy. I have Wagner for all of them. I have Wagner for all of them. This box is regular. And the argument with the mass is the same as for the single energy. Nothing changed. The difference is that I have this estimate. I can assume the disjoint boxes here, they're all, every energy, I only have at most a certain number of paired boxes, which I estimated by taking an even number of not allowed boxes and using the independence. I use this Wagner between boxes to say that I guarantee Wagner in one of them for every energy, and one of them is going to be good. I can never say both are good, but one of them is good. And that's all I care for. And that actually proves the result. So what we prove here was that the probability, so I had x minus y bigger than L, that was the induction hypothesis. The probability that for every energy in this particular interval, either one or the other is, the M is going to change as before, but we can control that as before, is what we want. Now, remark, and I'm not going, I can't lift that one. Okay, and that's not the first time I tried it, by the way. Okay, so the point now that I want to say is that at first, what I actually show, and that's how these things used to be stated, is that I can find scales Lk of gamma, k equals 0, 1, such that I have this statement with a k, right? For every k. The point I want to make, and this is actually a simple argument, but I am going to skip it. It's basically, I think, take a box L, I divide it in things maybe size L over 10, and then I require that the probability of all of them be good, which I can do it because I'm not, I lose a little bit, but I'm not trying to improve. and then I'm able to show, I divide these in things of size Lk as close as I can. I can actually show that this is true for every L bigger than some L0 that maybe is not the original. I have to go a bit higher, but I can remove the K and simply by, I have to change this, the probability. My parameters always change a little bit, but I can do to the case, which makes it convenient to see, to actually say I don't have to worry about Lk's. It's true for every L. These require a separate argument, but that's actually a simple argument when you do. That is not a complicated argument like the other way. It requires a little bit of technical work, but that's not going to help the understanding of the whole thing. And I want to go and finish by proving localization for the multiscale analysis. Okay? So I will stop here from the multiscale analysis, and with this we finish the proof of the theorem I stated at the beginning. And now what we have is that there exists L0 tilde such that for every L bigger than that and x minus y, I have, and I manage in the end to have some m which is the same for all of them, m is positive, so that I have a statement like this. And my interval now only needs, I did it for this small interval, but let me now take these as hypothesis. We proved a small interval, but suppose we have that in some bounded interval. It doesn't matter what the interval is anymore for us. Okay? Now, I want to extract localization from that, because we didn't do that just to have fun doing all these calculations. And if you want a joke, it's a joke about Barry. I can tell you that the first time I did this thing, when I did the work with Dreyfus a long time ago, I went and I gave a talk, you probably have heard that one, and I gave a talk at Caltech. And Barry looked at it and told me, and I actually called my talk Localization Without Tear. Localisation sans pain, that's the translation of, but in English they translate without tears. And Barry looked at me at the end and said, I think your title is misleading. The full expense stuff felt like a root canal, but this still feels like I went to the dentist. This is not this, a much simpler version. Okay. So now, So now I'll take this, my hypothesis, and to make my life simpler, let me give a name for this event. This is a set of omegas, right? The set of omegas such that for every energy, either this box or this box is regular. And I'll call this set are the relevant parameters are M, L, I, X, and Y. So that's just notation for this set. And so what I have, the probability of this event is bigger and equals than 1 minus z to minus L to z zeta. And I can do it for every zeta. I probably should put the zeta here. The L0 tilde depends on zeta, the mass depends on zeta. But I can do it for, I can get as close to exponential, but I cannot get exponential by this method. This does not give exponential because we use the Wagner inequality. If you can, all right. So first, I want to prove Anderson localization, by which I mean pure point spectrum and exponentially almost with probability 1, with probability 1 on the interval I. Claim that once I have this statement, I can prove localization. So how we do it? So I thought today would be better to concentrate in that part and not in more of the details of that. So let me fix the zeta, which I get there. And let me take a box which I'll now simply center at 0. Could center it anywhere. So I have this box. And I am going to take a covering of these boxes for box of sizes L over 10. So I consider what I called C of L, L over 10 of 0, which is a collection of boxes of size L over 10 that cover these boxes in the appropriate way. And I am going to consider the event, let me call it AL because the 0 is going to be fixed now. I am going to take, okay, so let's call U the center of one of these boxes. So let's take me one of those boxes. I should put M of zeta, but I'll forget that. But let me take L over 10 now. I, 0, U, right? Let me take these events and let me take the intersection. Now, these U's are centers of the coverings of the box of size L. I should put a 0 here if I want to be totally consistent, or boxes of side L over 10. So these are not in a very different scale. I'm not playing a game of scales now. These are small. I don't mean I need 10. But let me not do all of them. I'll only do for them that are bigger, or little bigger than little L over 10. And actually, I think probably L over 20 is enough. I just want these boxes to be disjoint to the box of L over 10 at the center. Probably L over 20 is enough, but I don't care. Okay, I can do that. And I can calculate the probability of the complementary event. I have the intersection of the complementary event is a union of the complement, right? So I conclude that the probability of the complementary event is less than equal. Now, the probability of the complementary event of each one of them is this. Oh, and I should say I took L over 10 to be bigger than this L0 tilde for the particular zeta I'm working on. I need my boxes to be big enough to have meaningful statements. Okay, and how many of them have? Well, that's a usual number in the covering. That's an overestimate. I don't care if I'm not taking all of them. But this number here, in this particular case, is just L over little l is 10. So this is 20 to the power d, right? Okay? Well, this means, so let me then call n infinity the limit, limit sup. Let me just see what I wrote, what one I want, limit it. So that means the limit inf of this set. Okay, no, I didn't. One step. I'm trying to go too fast. So I have that. Okay. So now let me fix a scale L, which I'm going to call L0. So this is bigger than this, so I can do all of these things. And let me define new scales by simply doubling them. I'm just doubling the scales, and I'll call AK to be the event correspond to L of AK. And I know that the probability of the complementary event to AK is less than or equal than clearly the summation of the probability of these complementary events is finite. They converge very fast. I use Borel-Cantelli. And the Borel-Cantelli lemma implies that the probability that AK eventually happens is 1. Actually, let me move to this so I can let the other stuff on the board. Good. Good. I'm okay. Okay. So I want to so this event, which I'll call infinity, which is usually written as the limit of the event Ck, and if you are interested, that's the Borel-Cantelli. Just for completeness, you take the ends, you take intersection n goes from k to infinity, and it takes a union from k to n. So there is an event, same thing, AK eventually happens. And what this means is that if omega is a infinity, there exists some k of omega which is finite, such that omega is the union, is the intersection of those. Omega is in AK for every k bigger and equals than k of omega. That's what means it eventually happens. That's the probability one. Okay. I will use it when I come. Now, I use to digress about eigenfunctions or generalized eigenfunctions, which I think that Wiedemann has discussed, so I don't have to do it. Okay? And I don't know if he already did the inequality I want, and then I don't have to do it either. But here I have h, which one of the h omega. This is a deterministic argument. And suppose I have h phi to be E phi. I don't want phi to be identically 0. Then, and by this I mean, since I'm working the lattice, it's easier. What it means is that at every point, when I do the procedure to calculate this number, I get this number. If I continue, you have to be a bit more careful. But here is just satisfies the equation pointwise. So now let me take lambda to be some box, and let me take, I take the restriction to the box, and I take an energy that is not in the spectrum. And what do I have? I have that 0 pointwise. 0 is h minus e applied to phi, right? That's the same equation. If this is 0, I can multiply by the characteristic function of lambda, and I still have 0. But now I want to rewrite phi as phi of lambda plus phi of lambda complement. Phi of lambda for me is chi lambda times phi. I'm restricting to this box. And if I do that, I'm going to get here h lambda minus z phi of lambda. And I'm using the decomposition now that L2, that I can write little L2 of the whole thing as little L2 of lambda plus little L2 of the complement, and this is a direct sum. I still have this here, so this is 0. And then I have the other term. And the other term is chi lambda. Now I have this term which lives on the boundary of lambda in the whole of CD, so I don't write. And here it comes phi, and it's really phi complement because of the property of Laplace. So I have this equation. Since this condition is simply telling me this is invertible, so I can write the operator, and I get that phi of lambda is minus h lambda minus E inverse. This is already cancelled, this times gamma of phi of lambda complement. In particular, maybe, where do I do that? In particular, and if I take x to be in lambda, I conclude that phi of x is minus this whole thing calculated at x, and it turns out to be, when you do all the calculations, here you have this gamma times the restriction is to the complement, and this is the inner product actually in L2 of lambda, because this thing also lives in L2 of lambda. Remember that to calculate something at x, I just take its inner product with a delta function at x. Things are easier on the lattice. Okay? So, what does it mean? That phi of x I can rewrite. This is a Green's function, summation of g lambda, that's this energy x u phi, I should put absolute value, phi of v, where I'm summing really as before as all points uv in the boundary of lambda. That's similar to what you have done before. I mean, using the property of Laplace, this is minus 1, I only across the boundary, 0 elsewhere, so you get this thing is well known. I mean, and I want, however, for my purposes, to rewrite it in something a little bit different. I'm going then to rewrite it as the same sum. Let me take the g lambda here. This I'll use it. Now, this is bounded by, okay, this is bounded by its L2 norm, which is 1, but not 1, it's an eigenfunction. I will now require, to simplify my life, I'll call t the operator of multiplication by x to the nu, where nu is something bigger than d over 2, which will be fixed. And generalized eigenfunctions means that this norm is finite. The little L2 norm or T inverse of phi is finite. That's a generalized eigenfunction. I think that's the same thing that David did.
So phi is not in L2.
No. It's a generalized
At
eigenfunction.
some point you said phi is bounded by its L2 norm.
No, as I said, no, it's not correct. Yeah, made a mistake. You are correct. No, phi is not in L2. The whole point is to prove phi is in L2. Now, phi is not in L2, so I took here and I put this hypothesis. Okay? And as David told you, the points where I have, with respect to the spectral measures, there is no difference between the spectrum of the operator and the collection of generalized eigenvalues. And so I put here, I could simplify if I centered it, but I will do it. I want to center at 0 for the moment, but I pay a price because every point here, V is here, right? So this distance is L over 2 plus 1. So here I should put a factor of L over 2 plus 1 to the power nu to compensate by putting the T here. But with this is finite. Okay. Okay, now this is fine. This is fine. Or, and if you prefer, this is fine. So now we're going to use it. Do you want to have a break, or do you want me just to go on and finish earlier?
To me, it looks that you're one step away to showing it is normalizable. So.
Yeah. Yeah, I am. I'm almost there. Okay. So now, let's suppose okay, now actually the way I want to work, let me go directly to the work. So I had omega in this set infinity. So I had kw finite such that omega is in ak for every k bigger or equals than this one. So the first thing I want to show here, one, and remember that what the conditions you had here, you have my box of size Lk, and then at the center I had a box of size Lk over 10, and then I had other boxes of size Lk that were around here, for which I know that either these or these are bad, either these or these are bad. In particular, if this is bad, all the other ones have to be good. And that's what I want to show. And the first thing I want to show is that if phi is not identically 0, there exists some k tilde that depends on phi and omega. That's called k tilde, such that for k bigger than k tilde, I claim that Lk over 10 of 0 is not M-irregular. Because I have a generalized eigenfunction, I cannot keep on expanding my boxes until they are big enough. Now, I am in the lattice, and in the lattice, phi of 0 could still be 0. So, since this is not 0, I can find x0 in ZD. Phi of x0 is not 0. So, I take k double tilde bigger and equals than kw and k tilde. And I also want L0 inside it, so I'll get, I want the 2x0 is less than Lk over 10. So my situation is that I have the box at 0, I come here to x0, and then I take something of Lk over 10 such that x0 is still a distance Lk over 10 from its boundary. And then I use the regularity and that equation, and this tells me that phi of x0 has to be equal, well, I go through the boundary, and then I get here the distance from x0 to the boundary, which is at least Lk over 10 divided by 2, so 20, if I didn't make a mistake with this calculation, okay? And then what I would get, oh, okay, I have this factor of Lk over 20 plus 1 to the nu times this. I'm getting this from here. But notice this is of course Lk. I have exponential here, this is fixed, this is polynomial, this is fixed, this goes to 0 when k goes to infinity, right? So this concludes that phi x0 equals 0. You can say, well, I showed that the limit goes to 0, but can I show that it never happens? Well, it never happens because you can say if k is large, this is always small. And if I had a sequence where this is regular, this would happen in that sequence, which is a contradiction. So I conclude that this is not regular. If this is not regular, I know, okay, so what I conclude is that there exists k tilde depending on everything, such that for k bigger than k tilde, we have that this box is not M-irregular, but then, since omega is in AK, these imply that all the boxes Lk over 10 of U are M-irregular for all U in this. L over 10, Lk over 10, and U is away from 0. I think I said Lk over 10 is fine enough. That was a conclusion. But then we can show that actually phi has to be in L2. That's the whole point of the exercise. I can show it's still in L2. So what I do is that I take a point x, and I'll take x to be bigger than LK double tilde divided by 5, which depends on omega, depends on my eigenfunction, so not right. And then, if this is true, there exists k bigger than equals than k tilde, so Lk over 5 is less than equals to x is less than Lk. I then take the corresponding box Lk of 10, I'm using the box Lk, for the point x, so that x is the distance Lk over 10 divided by 10 from the boundary. So this box is M irregular, because these are all R. But if these are M irregular, I use this equation again. Well, I have SD Lk over 10 to the d minus 1. The distance to the boundary is e to the minus m Lk to the 10. And then I'll get the same thing here, Lk over 2, 20 plus 1 to the nu times s. Okay? But clearly this is less, 100. 10 divided by 10. I should take Lk, 10 divided by 10. This should be Lk over 10 divided by 10, because I have a box of size Lk over 10, and then when I take a point, the distance to the boundary has to be at least this divided by 10. So I get 100. Not very important, so this Lk, let's say, over 200 times this for large L. But now I can only I have to replace Lk for something smaller. Norm of x is smaller. This is less than or equals than e to the minus m. Norm of x t inverse of phi. So what we concluded is that for every x bigger than equals than some number Lk, and this depended on omega and depended on the energy, depended on nu, but nu is a fixed parameter. It didn't depend on phi, it only depended on the eigenvalue. I have that phi of x is less than equal than e to the, what did I say, 200, right? Times this. On the other hand, phi of x, I have a bound. I can look what happened when x is less than or equals than 5 divided by 5, I think. one can happen is divided by 5. This would be less than or equal than, if I use this, I think this would be less than or equal than LK double tilde over 5 plus something like that.
Now you see from the first inequality, that's not that's in L.
No, what I'm saying is the following. I have estimated this. Here's here. Here is LK double tilde divided by 5. If I take x outside, I have a bound.
Yes. And inside there are finitely many values. So there is a
I know, but I want my bound to be uniform in all the phi's with the energy E. If I have an infinite number, they may not. I want to extract finite multiplicity of eigenvalues. So, and that's not hard from here, simply because of this factor. So now what I'm taking is that, let me take x to be actually inside this box where I don't have the estimate. What can I say? Phi of x, if you look what that is, I can put this at that value, but I have to make the correction. And the correction is going to be smaller than whatever this is. Do I need, maybe I don't even need a plus 1 here to the power nu. Or maybe there is a plus 1, I'm not going to bother, but okay? And the conclusion putting these things together is phi of x is less than or equal than some constant that does depend on omega, does depend on the energy, but it doesn't depend on the particular phi for this eigenvalue. And I have the generalized eigenfunction norm, and I have the decay. I can use the same, I just compensate with that constant, of course, make it bigger, m, so let me call some m tilde x, which is this m over 200. So, my conclusion is that phi generalized eigenfunction with corresponding eigenvalue in I implies that phi is in little L2. It's exponentially decaying. So this means that E is actually an eigenvalue. So all generalized eigenvalues are eigenvalues, so I conclude that H omega has pure point spectrum in the interval I. Huh?
That's a good point where at or near at you may want to have a break from.
Yeah. The only thing here is that I have to sum this, but I can do that after the break. So you want a break or you want to finish earlier? I can do either way.
Well, it's just some remark on what you have done, or is there some other derivation?
No, there is something else I want to do. I have one more remark on this, and then I want to do one more thing.
Just a short remark, which fitting to that, together with that, and then let's have the break.
Okay. So the remark from that from here I can get finite multiplicity of eigenvalues, is that in this interval, because this is just a consequence of that. Where did I put it? Okay. So now I want to put finite multiplicity of eigenvalues. And so I want to show now that if omega is still in that set, right, probability 1, that for all energy in I, the trace of p omega of E, and for me this is eigenprojector at energy E, I want to show this is finite. But it will follow from this because let me take phi j. I already know I have two-point spectrum, right? So let me take phi j to be an orthonormal basis for the range of this project. So these are an orthonormal basis for all the functions, for all the eigenfunctions with eigenvalue E. Then clearly, I'll forget the omega. This is a sum of the orthogonal projections over pi j. So these are one-dimensional project. If you prefer, this in the standard notation, I think is this, right? And then it's just an easy calculation. To obtain the finite multiplicity of eigenvalues, it's fine. And the calculation, is simply the following one. Well, let me look, take any point x in ZD, and look into this. Well, this is summation in J of phi j of x squared, right? But now I use that estimate. This is some constant square. This constant depends. Oh, I'm sorry. I said something that this depends in omega, but this does not depend on the energy. This does not depend on the energy. I made a, no, that's correct. Let me see. No. Okay, let me see if this. It doesn't depend on the energy. It depends. But I come here. What I want to say is that I'm going to sum. I get a constant c squared. This depends on omega, but it doesn't. Oh no, it depends on the energy. But the energy is fixed. I'm sorry. It's a long day. The energy is fixed. It doesn't depend on the energy. Let's write what we have. We have minus 2 m tilde of x. Then I have simply T inverse of phi j squared. So it's c squared. This depends on omega, depends on the energy. E to the minus 2m x summation in j of T inverse of phi j square. But if you look in what this is simply the trace of T inverse P of E T inverse. And I can bound it by some constant that depends on u and is a bounded interval. That's just a trace estimate. It's no decay, just a trace estimate. There is a uniform estimate for that. Usually you do with the resolvent, and then this is a bounded function. And once you have that, I come here, I write the trace of P of E. This is summation in x, delta x, P of E, delta x. I use this estimate. This is finite. Okay.
Now I think it's good time.
You got that 5 minutes there.
Are there any questions before we go into that?
Yeah, I have one more thing I want to say.
Is that also?
Huh?
That looks like a typical lattice calculation. It's also
Well,
or not?
this one, to prove this to me, that this is finite. The way
The whole thing. The
The-
finite multiplicity.
where this comes, let me see the continuum. The continuum, what you usually prove. Take something outside the spectrum, say below, minus some c, some k, which is below the spectrum. You need some power. This power is going to be, I don't know, d over 2 plus epsilon, or d plus epsilon, I forgot here. And you prove this is always finite. That's a trace estimate. Or if you prefer, we prove that if you take the characteristic function of a cube, this is finite, and the estimate is independent, so the other thing is summable. This is a standard thing. This is true in the continuum.
Continuum.
Yeah, it's true in the lattice. The lattice is easier.
The lattice you wouldn't even need the result.
You may not need to do that. It's probably trivial to just do it directly. I'm still thinking in terms of the continuum. But the estimate is true. And the lattice, actually, he's right. In the lattice, you have nothing to do.
I estimate that by one.
By one, and you just sum the things. Okay, it's trivial. And what comes when the energy is, so this depends actually not only in these, but in the soup of the interval. In this case, actually, it doesn't depend on the soup of the interval. In the lattice, actually, I can throw this away, right? In the continuum, it depends on the soup of the interval, I'm thinking there. So these proofs are developed in the continuum, actually. So the point is that using the generalized eigenfunctions technology, you can control those sums and what comes up and get something finite. That, I think, is the simplest proof of simplicity of eigenvalues that there is. In the lattice, we can actually get a bound, but that uses Minami estimate, and it's a different. It's not for in the continuous. They don't have. This is not done through the multiscale analysis to improve on that. I can use that. If this result is true in the continuum, it's finite. It is true for Bernoulli. It's the same. But that's the proof for Bernoulli. Also, that once you get the decay of the eigenfunctions and so, I mean, you get that the decay of, you get that the trace is finite. Trace for a single eigenprojector is finite, so we have finite multiplicity of eigenvalues.
Good. Let's have a break. 5 minutes.
Okay, to do.